Hello and welcome to this lecture. In this lecture, we're going to see examples. We're going to continue with the previous examples. We've been seeing examples in a row. We saw examples for diagonalizability. We saw examples for finding the diagonal matrix with respect to the eigenvalue basis, eigenvector basis. Now we're going to see powers of the matrices. Okay, so once you find diagonalization, finding powers is trivial, right? So I'm going to just show you explicitly how that works. Okay, so here is the first example: 1, 2, 3, 1, 1, 1. And for this particular example, if you remember, in a couple of weeks ago maybe, we actually found the a power k, right? So we used all sorts of summing formula, AP, GP, all sorts of guessing, and we found what a power k was. So now I'm going to show you how to find a power k using diagonalization. And it's very simple. You don't need to remember some fancy summation methods. You can just directly do it. Okay, how do you do it? We know that a can be written as S d S inverse. And S is this guy, this column of eigenvectors of A, and then D is a diagonal matrix with 1, 2, 3 showing up only in the diagonal. S inverse you have to find. Okay, so this is one task that you have to find. Okay, so I'm not, you know how to find, right? So once you have S, you know how to find S inverse. In small cases you can find. In this particular case, S inverse ends up having this very, very small, simple form. Once you have S and S inverse, it's very easy to find a power k. So notice what I do here. A power k is nothing but S times d power k S inverse. Now d power k is trivial, right? S and S inverse already I know. D power k is very easy. It's 1 power k, 2 power k, 3 power k. That's it. There's no other summation to evaluate, nothing. For diagonalizable matrices, it's really, really trivial to find powers. Okay, so you have 1, 2 power k, 3 power k. Okay, so finally when you do this multiplication, you get this answer, which is 3 power k minus 2 power k, and you can check if you put k equals 1, you get 1, 2, 3, 1, 1, 1. Yeah, this is correct. Okay, so it's a simple enough answer, and this something we derived very in a complicated fashion earlier. We're able to do it in a very simple way because of our ability to diagonalize matrices. Okay, so let's see the next example, which is 1, 1, 3. Again, the same thing. I think once you see one example, you'll see the other examples are trivial, right? So you just write, you find the S. The only task is to find the S inverse. Okay, just finding this S inverse is a little bit of a task. You have to just know how to do inverse. We've already seen enough methods for finding inverse. So once you do that, a power k is just trivial. You get the answer. Okay, so I hope this is okay. I hope I've not goofed off on any of these calculations. Please check it again. If there's a mistake, you can comment on the discourse forum. Okay, so here is a 3 by 3 example. This also is something that we saw earlier. We looked at the patterns and we identified what a power k is. You go through the diagonalization process, you get to the answer in a very, very trivial fashion. Once again, from S, finding S inverse is the only non-trivial task here. Okay, so okay, you found powers. You may ask, what's the big deal? So it turns out finding powers of matrices is central to system theory, control systems and so many other systems theory. In particular, stability is a very, very important aspect here. So how does that work? We saw already in some examples that a state of a system, usually in time n, is represented by a vector. And this state evolves from time to time. From time n, it evolves to n plus 1, etc. And that evolution usually is captured by a matrix multiplication. Xn plus 1 is A times Xn. Okay, so it's very common. This A could be a constant matrix. In many cases, it is. Okay, this A could be a k by k. It will be a k by k matrix, right? So the Xn is a k length vector. So A will be a k by k matrix. Okay. So now what happens when this when you look at this evolution from time 0 to n? Okay, time n to n plus 1, I know it's A. What happens from 0 to n? It's very easy. Okay, so xn is a times xn minus 1. Okay, just using this formula, which is the same as a squared times xn minus 2. Do you see that? Because I can write xn minus 1 as another a times xn minus 2, and a into a is a squared. Now you keep repeating this, you'll see that you get a power n into x0. And this n can keep growing very, very large, right? So you don't, you want it for all time. Okay, and so this xn is a power n into x naught. So if you want to worry about xn, if you want to compute xn, or if you want to know what xn is, how does it behave, then you really need to know how a power n behaves. So finding a power n is very, very central to all sorts of system theory. In particular, many people are worried about stability. What is stability? You may start off with x naught being finite. Okay, so typically the first initial state of the system is finite, and then the system starts evolving according to this a, and a system is said to be stable if, when x naught is finite, xn is also finite for all n. Xn will not blow up. Okay, in many of our previous examples, we saw when we raised a to the power k, you got scary terms like 3 power k, 2 power k, and all that. Okay, so all that should not happen. This a power n should not blow up. Okay, so how do you make sure that a power n does not blow up? Here is where diagonalizability helps you in a tremendous fashion. In fact, even if a is not diagonalizable, you can say a lot of these things, but I'm not going into detail there. We'll start with the diagonalizable situation. If a is diagonalizable, then you know I can write a as SD S inverse. Not only that, you know the elements of D, right? What are the elements of D? These are going to be the eigenvalues. I'm going to write counting repetition, maybe lambda 1 to lambda k, and I will order it in this fashion. Mod lambda 1 is greater than or equal to mod lambda 2 greater than or equal to so on mod lambda k. So this is very common. You go from the largest eigenvalue in absolute value to the smallest eigenvalue in absolute value. This is one very common way to sequence the eigenvalues. Okay. So once you do this, a power n is very trivial, right? So s times the eigenvalues in the D alone get raised to the power n, lambda 1 to lambda k, S inverse. So now we can start answering questions like stability, right? So what is xn? Xn is a power n into x naught. X naught is finite. My only problem is if a power n is going to blow up. Now what part of a power n will blow up? S and S inverse are just constants. They don't change with n. Okay, so they are just constants. Only this D matrix can blow up. And what controls the blowing up of the D matrix? It's lambda 1 to lambda k. And what controls the blowing up of real numbers? It's whether this absolute value of lambda 1, in fact, absolute value of lambda 1 is the largest, right, in all this. These are not real numbers, this could be complex also. So you have to worry about absolute value, but is the absolute value greater than 1 or less than 1 is the issue, right? So in fact, you can see system is stable if the largest eigenvalue lambda 1 satisfies mod lambda 1 less than or equal to 1. Okay, in that case, it will not blow up. Okay, so this is a very, very common condition in all of system theory. So you'll see whenever there is a matrix and you're figuring out how to control its evolution, you always worry about the eigenvalues. Are the eigenvalues less than 1? If they're less than 1, then less than or equal to 1, then they end up being stable. In fact, if lambda 1 is strictly less than 1, you notice that all these guys will go off to 0. So this middle diagonal matrix is going off to 0, so which means xn will definitely tend to 0, which is also a good thing. You may want your states to finally go off to 0. Okay, quite often that also is expected. So if that is true, then your mod lambda 1 better be strictly less than 1. Okay, if it goes greater than 1 or equal to 1, then maybe your xn will not settle down to 0. Okay, so this is a application for how powers of matrices are used. So many other places where this shows up, but this is a central way in which the eigenvalue and diagonalization are used. Now supposing your matrix is not diagonalizable, then it turns out you can evaluate a power n almost with the eigenvalues except those ones that I showed you, and there are ways to control how those things are raised to powers and all of that. Okay, so that concludes sort of all the examples I wanted to give. Let me close with a few problems. I won't, maybe I will describe some of the central ideas in this problems, but maybe not work it out in great detail. So the first one asks you to evaluate the powers of the following matrices. So here is something that's given 1, 2, 2, 1, 1. So whenever you have a structure like this, pause and give it a little bit of a thought. Okay, so notice if you see here, so here you have some sort of a diagonal expression here, but this is like a 2 by 2 matrix, and then there are zeros here, and then there is a 1 here. Okay, so if you have a structure like this, right, so where you have a square matrix here and a square matrix here, these two are square, and then here all is 0. Okay, so this is A, B, so let's say this A is K cross K, and this is L cross L. Okay, so overall you have K plus L cross K plus L. So if you raise this matrix to the power n, you will simply get A power n 0, 0, B power n. Okay, so this is some sort of a block diagonal matrix property. Okay, so whenever a matrix is block diagonal, you can simplify some of your work. So this is very important. So here if you notice, you've got a block diagonal structure. So anytime you have a block diagonal structure, if you raise it to the power n, it's enough to raise 1 to the power n, which means 1, right? So this will be just 1. And then you only have a 2 by 2 matrix you are raising to the power n. So you don't have to deal with the 3 by 3 matrix. It's enough if you deal with this 2 by 2 matrix, and 1, 2, 2, 1 power n you should be able to do, right? So it's 2 cross 2 matrix. It will have an eigenvalue. You find the S, you find the S inverse, you find the D, you just raise to the power, you'll solve the problem. Okay, so this is very, very easy to do. So here is another 2 examples. Both of these examples also follow the same sort of principle. So you've got a block diagonal structure. The block diagonal structure is very important. So you don't need to deal with a 5 by 5 matrix here or a 4 by 4 matrix here. It's enough if you deal with a 2 by 2 and a 3 by 3, you will get to the answer. Okay. So I hope this is a little bit illuminating and it helps you. Okay. Okay. So here is another question. So evaluate the eigenvalues, eigenvectors and powers of the following matrices. So this matrix is 2, 2, minus 2, 5, 1, minus 3, 1, 5, minus 3. So I'm going to do minus lambda along the diagonal. I'm going to compute this guy. It will look a little ugly, but finally you will be, I hope, surprised by the answer that comes out. And I hope I don't goof off and make a mistake. If I don't, you will get something very nice. Plus 15, and then let me write it a bit more cleanly. And then you've got minus 2 times 5 times minus 3 minus lambda plus 3. Hope that's okay. And then minus 2 times you've got 25 minus 1 minus lambda, right? So this is a bit interesting. So you get here, I'm just trying to see what's the best way to do this. Let's just do the multiplication 2 minus lambda, and I'm going to get here lambda squared, and then I'm going to get 3 minus 1, 2 lambda, and then minus 3 plus 12 here, that's okay. And then this minus 2 can be taken common outside, and then, okay, anyway, you can do the multiplication, I think. So you get 10 lambda, and then minus 15 minus 12 plus 24, I think. I hope that's correct. Okay. And then you've got minus 2 into 24, so minus 48, and then minus 2 lambda. I hope that's correct. Okay. So this is what happens here, and then if you multiply this out, you will get, very surprisingly, you will just get minus lambda power 3. Okay. So you can check it out if you don't believe me. All the other terms should vanish. I think it should happen if I did it correctly. So 2 lambda square minus 2 lambda square term goes, and then 4 lambda minus 12 lambda is 8 lambda, and this is same minus, no, this is minus 8 lambda, so this is plus 8 lambda, it goes away. Then you have the plus 24 plus 24, 48 minus 48 goes away. Okay. So this matrix A, though it looks spectacularly complicated, has got repeated eigenvalues 0. Okay, so this guy has got 0, 0, 0 as the eigenvalue. So now it may or may not be diagonalizable, but you know from our experience that even if it's not diagonalizable, I can create an upper triangular matrix with 0, 0, 0 and some 1 showing up right below by cleverly doing it. So you will have a triangular matrix, and if you raise it to the suitable power, it's going to go off to 0. Okay. So let's look at the last example. This one looks really confusing. So if you see, it's got 1, 2, 2, 1, 1, 1, 2, 2, 2, 1, 1, 2, 2, 2, 1, 1. Wow, looks a little confusing. How do you find eigenvalues, eigenvectors, powers? First thing you can look at is you should see if there is some rank type constraint here. So I think if you see, first thing you can see is the row sum, right? It's all equal, right? So the row sums are equal. So there will be one eigenvalue 6, right? One of the eigenvalues will be 6, the sum of the row, and 1, 1, 1, 1 will be an eigenvector. Okay, so that's one inference you can make from this situation. That's one guy which you can do. The second one maybe so if you see the sum of the first and third column, right? If you add the first and the third column, you're getting 3, 3, 3, 3. And if you add the second and the fourth column, you're again getting 3, 3, 3, 3. Okay, so there is like an obvious linear dependency here. So in fact, if you do first column plus the third column minus the second column minus the fourth column, you will go to 0, right? So you see that there is so if you do rank calculation, you will see that nullity will be greater than 1, greater than or equal to 1, it may be 1. So which means there is a 0 eigenvector hiding somewhere, right? So you can find that the eigenvector is like, 1 minus 1, 1 minus 1. Okay, so that 1 minus 1, 1 minus 1 is an eigenvector with eigenvalue 0. So, you've got an eigenvalue 0, you've got an eigenvalue 6. So, you found 2 eigenvalues. So, once you find 2 eigenvalues, the remaining are also not too difficult to find. Okay, so you can find. If you have to do a brute force calculation, you're going to get a degree 4 polynomial in the determinant a minus lambda I. You already know 2 roots. You can find the 2 other roots quite easily. So that's also possible. Or you can do trace and determinant. So it's also a very powerful idea, right? So you got 2 eigenvalues. One is 0, another is 6, and then the trace is 4, right? So you see 1, 1, 1, 1, trace is 4. So for the remaining 2 eigenvalues, the sum should be 4. Okay, so here is a way to think of this example. So maybe I should do this example in some detail here. So you've got 1, 2, 2, 1. Later on, you'll see that there are other clever ways of doing for this particular problem. But anyway, knowing what we know now, we can do this. So clearly, 6 is an eigenvalue. And the eigenvector corresponding to that is 1, 1, 1, 1. And then 0 is an eigenvalue, and the eigenvector corresponding to that is 1, minus 1, 1, minus 1. Okay, so I hope you see this. And then trace is 4, which means if you have another 2 eigenvalues lambda 1, lambda 2, lambda 1 plus lambda 2 plus 6 plus 0 equals 4. Okay, and then you have to find. Determinant won't help you. Determinant will end up being 0. So on the powers product of the lambda will be 0. So you've got 2 eigenvalues. Their sum is 4. I don't know if there is any other clever way to do this. I don't think so. You have to find the characteristic polynomial and then work with it and get it, because the other 2 eigenvectors and eigenvalues, these 2 I think are complex. Okay, so maybe. Right, so it's a little bit more complicated. So you have to find the characteristic polynomial. 6 is a root, 0 is a root, so you'll be able to factor out. So you'll get only a degree 3 characteristic polynomial, right? You'll get lambda times some lambda power 3, for which 6 is a root, so you can factor that and you can get to the answer. Okay, so it's a little bit of a complicated mess to work these kind of examples. Later on, we'll see a simple thing. This matrix has the circulant property. So you can use the circulant property, you keep right shifting, you get something. So by using the circulant property, you can do this problem in a much easier fashion. Okay. So anyway, so hopefully these kind of ideas are a little bit interesting. You can find powers and eigenvalues and eigenvectors in very non-trivial fashion. Okay. Thank you very much.